So now we're going to sketch a graph of that famous kind of curve called a hyperbola. We're going to do a hyperbola exercise. And everything you need to know about hyperbolas is on the starts with this video and is covered by the handout, the typed handout on hyperbolas that you can see before you that's available in Canvas. The previous video of theory is available if you want more details about where the equation comes from, but you don't need to watch the theory video if you just want to focus on the exercises that I work through in this video and the following. So a hyperbola is a special kind of curve. It's related to an ellipse, but it's different in the sense that every hyperbola has two branches, two separate pieces. And every hyperbola also has two important lines related to the hyperbola called asymptotes. The asymptotes are these dotted lines in the pictures I've drawn on this handout. There's also something we're going to talk about called the central rectangle. You kind of see this dotted line going around this rectangular shape in the center of the graph. And we'll talk about what that means when we start working on an example. So one thing you'll want to remember about hyperbola too is it only has two intercepts, either on the x-axis, like this hyperbola here, or there's a hyperbola here that has two intercepts on the y-axis. So it's different from an ellipse because we've seen how ellipses have four intercepts, two on the x, two on the y. And the equation of a hyperbola looks very similar to the equation of an ellipse, but it's different. And it's always going to be this minus sign between the two fraction terms that help us recognize that we're dealing with a hyperbola and not with an ellipse. An ellipse always has a plus sign in between the two fractional terms. And also there's the idea of the two foci of the ellipse. If we want to find the foci, there is an equation that relates the a, b, and c constants. It's a little bit different for a hyperbola, though. It has the form a squared plus b squared equals c squared. With an ellipse, we saw that this equation had a different form, a squared minus b squared equals c squared. And you'll be able to refer to your notes. You don't have to have that memorized, but just be aware that that equation is different for a hyperbola. It's different from the equation we use with an ellipse. So let's go ahead and start an example. So the examples are on the second page here. And we're going to sketch a graph of x squared over 9 plus y squared over 4 equals 1. We have to label the vertices, asymptotes, and foci, and we also have to find the equations of the asymptotes, and we'll go through that as we work our way through this exercise. So I just summed it up here on a separate sheet of paper. So the first thing we want to do is find the intercepts. And you don't have to know ahead of time if the intercepts are on the x-axis or on the y-axis. If we look, let's just look for them, both x-intercepts. If we set y equal to 0 in the equation, then I'd be writing x squared over 9 minus 0 squared over 4 equals 1. Kind of similar to what we do with an ellipse. Notice that plugging in 0 for y makes this whole fraction equal to 0. So I'm just left with x squared over 9 equals 1. X squared is equal to 9. So when I take square roots, x is plus or minus square root of 9. So x equals plus or minus 3. Looks like I have two x-intercepts. I have 3, 0, and I have negative 3, 0. Now, if I try to find y-intercepts, what's going to happen here? If I set x equal to 0 in that same equation, just notice the difference here. I'm going to have 0 squared over 9 minus y squared over 4 equals 1. This 0 squared over 9 is just 0, but I'm left with minus y squared over 4 equals 1. If I multiply both sides by 4, I have minus y squared equals 4. And let's take this equation now. Because we have a minus sign, I'm going to multiply both sides by -1. That's equivalent to saying y squared equals -4. When I take square roots, I get y equals plus or minus the square root of -4. And notice that there are no real number solutions. No real number solutions, because I'm trying to take the square root of a negative number. And now there's an interpretation using I and imaginary numbers for this, but remember, imaginary numbers do not appear on graphs. So what this is telling us is that there are no y-intercepts. And I had a graph grid set up. Just want to start getting ready to draw a graph. So what we know about this hyperbola is that it has intercepts on the x-axis at 3, 0 and -3, 0. But it has no intercepts on the y-axis. So I kind of have an idea. I'm just going to already of the shape. Make that draw a little darker in pencil. It's going to look kind of like that. And kind of like that, when we fill in the details, there's going to be a branch on this side, a branch on that side. Okay. But now, in order to draw the graph carefully, we need the asymptotes. And in order to graph the asymptotes, we're going to draw something called the central rectangle. And in order to draw the central rectangle, we're going to find the intercepts of the conjugate hyperbola. The conjugate hyperbola. And the textbook calls these the covertices of the hyperbola that we're looking for. And what you do is you take our equation, x squared over 9 minus y squared over 4 equals 1. And what we're going to do is we're going to change the order of the subtraction. So I'm going to write this as y squared over 4 minus x squared over 9 equals 1. Now, this is actually a different hyperbola. We've changed the equation. We no longer have an equivalent equation. It's actually called the conjugate hyperbola to the one we started out with. And can you see from this equation that now I can set x equal to 0 to find y-intercepts? And actually, I cannot set y equal to 0 in this equation. So the reverse happens here as what happened with our original equation. Now I can set x equal to 0. I'm going to get y squared over 4 minus 0 squared over 9 equals 1. I'm going to bring that over here to the side. I have y squared over 4 equals 1. Y squared equals 4. because I changed the order of the subtraction, I now get a positive 4 inside that square root. And I actually get y equals plus or minus 2. I get two solutions then, 0, 2, 0, negative 2. Those are my covertices. They're the conjugate hyperbola vertices. They're not actually points on our original graph, but 0, 2, I'm going to mark in a slightly different way, just put a little x there, 0, negative 2. They're going to be the points that I need to draw what's called the central rectangle, and that's going to lead to the rest of the details of this graph. So what I did was, to get those covertices, I changed the order of subtraction to get a different hyperbola, found its vertices. They're not points on the graph I want, they're points I'm going to use to help draw the graph. Okay. So here's at 3 and negative 3 on the x-axis, the vertices of the original hyperbola. Our covertices are at 2 and negative 2 on the y. Now, through each of the vertices, I'm going to draw a dotted line that's vertical through these guys. And through the covertices, I'm going to draw a dotted line that's horizontal. And that's how I draw. This is called the central rectangle now in my picture. The reason we draw the central rectangle is really to get the asymptotes. And we're going to get the asymptotes by drawing the diagonals of that rectangle from one corner to the opposite. This is really what we're after, these dotted lines. They'll always pass through the center, or through the origin, 0, 0. So there are my two asymptotes now. Now I can fill in a better sketch of my actual hyperbola. I know, again, my x-intercepts were at 3, negative 3. Now I'm just going to draw a curve approaching the asymptote as I rise up. And do the same thing as I come down. Make sure we don't forget we got 3, 0 as a vertex. Here we got negative 3, 0. And the other branch is just to the left here. Okay, there's my hyperbola. I got it sketched with the asymptotes and the vertices in the picture. So that 2 and negative 2 on the y-axis, they helped me draw the rectangle, but they're not actually points on the hyperbola that we want. Now there are two more things that we want to do before we're through with this problem. We want to find the foci. And we're also going to find the equations of the asymptotes. But first, let's just find the foci. And to do that, we use the a squared plus b squared equals c squared equation. The a and the b are just the denominators of the equation in standard form. Actually, these are a squared and b squared. So our equation, our original equation, is in the form x squared over a squared minus y squared over b squared equals 1. So my a is actually 3. My b is 2. Again, they match up exactly with the x-coordinate and y-coordinate of the vertices and the co-vertices. So a squared is 9 plus b squared is 4. That adds up to c squared. So 13 is c squared. Plus or minus the square root of 13 is c. So my vertices now are going to involve square root of 13, negative square root of 13. I need to figure out now, do these go on the x or y axis? Well, if the hyperbola is in this position, the vertices are going to be on the x-axis. So I know that in this example, the square root of 13 and negative square root of 13 are x-coordinates. And let's get a decimal for that. Square root of 13 is it's about 3.6. So negative 3.60. So 3.6 is there between 3 and 4. So I have a focus here at square root of 13, 0. Just write focus. And at negative 3.60 approximately, I have another focus here at negative square root of 13, 0. Another focus. Okay, so I put the two foci onto my graph. Notice that the hyperbola kind of wraps around, each branch the hyperbola wraps around a focus. Now, the other thing we need to be able to find are the equations of the asymptotes. Asymptotes. And they're always going to have a certain form. They're always going to have a form y equals mx plus 0, because we know the y-intercept is 0 for both asymptotes. So we don't, again, all we need to do is find the slope. And the slopes are going to be opposites of each other. So we're going to get y equals mx 0. We're also going to get y equals minus mx 0. So slopes of the asymptotes are opposites. So if we find the positive one, we can just take that negative to get the negative slope. Now how am I going to get the slope? I'm just going to figure it out using points. I'm going to pick a point at the corner of my central rectangle. X was 3 here, y is 2. This point is 3, 2. Remember, each asymptote goes through 0, 0. So this one asymptote, to calculate its slope, I can get the slope using 3, 2, and 0, 0. M is going to be the difference of the y's, 2 minus 0, over the difference of the x's, 3 minus 0, is 2/3. So one of the asymptotes is y equals 2/3 x. Again, plus 0, because I don't have to write the plus 0, because the y-intercept is 0. And the other asymptote going in this direction. You can calculate the slope separately if you want, but you don't have to. It's always going to have the opposite slope. So the other equation is y equals negative 2/3 x, and it also has y-intercept 0. So here are my foci. Here are my equations of the asymptotes. I've labeled the foci. Let's just label the asymptotes in this picture. Y equals 2/3 x. And over here we have y equals negative 2/3 x. And I think I want this all to, let's get our equation back there and the graph. And we got it. We got it, a hyperbola graphed.